Anyone here who doesn't speak Hebrew or understand it at least? If not, don't be shy. The speaker can speak English also. Anyone who prefers English very much? He do know.
Okay.
Okay. In your honor, we do it in English. Okay. I will start the introduction in order to save time. Maybe more people will come. So all of you know Professor Abraham Kazir. He graduated, did both his undergraduate and graduate studies at the Hebrew University, doing his PhD in condensed matter with Mani and Halperin, and later doing his postdoc with Amnon Yariv at Caltech. He then came in 1977 to Tel Aviv and has been here ever since. He's been the head of much of the applied research in Tel Aviv, had scores of students and research people working with him. And I know this, I feel very bad that this happens during a strike, because there's been a tremendous effort invested in making this a nice and interesting show. So who is here will enjoy it, I'm sure. And the subject is quite clear here. Okay, and he deserves another congratulation for another thing.
Okay, thank you for the invitation to give the colloquium. And the topic, as you see, is on infrared transmitting fibers. And what I'd like to do is to summarize the work of our group during the last few years. And the topic deals with infrared. And infrared, as you see here, is somewhere between the visible and the microwaves. We do not see infrared. Our eyes do not detect infrared. But we are not the only creatures on Earth. And there are many creatures that do detect infrared. And some of them even can see in the infrared. They have like thermal cameras in their bodies which can get an image in the infrared. So let me introduce by describing what God in his wisdom devised for us. So these are some of the animals in the animal kingdom that can see or detect infrared. And these are beetles, insects, butterflies, snakes, and bats. And I'll briefly describe why they do it and how they do it. So this is one example. This is a beetle, and this beetle has infrared detectors in its front legs, somewhere here. And why does the beetle need infrared? Because when males and females mate, the females lay eggs, and they cannot lay the eggs in regular living trees because the larvae cannot survive in the trees. The trees reject them. So they're looking for forest fires and for trees that are dying, and then they lay the eggs in the dying trees. So they can detect the infrared emitted from a forest fire from a distance almost up to 100 miles. This is the detector, as you see on the side. And how does the detector operate? It's very, very clever. The detector operates by this. You see this part? This is like a small sphere which contains molecules that highly absorb in the middle infrared, between 3 and 30 micrometers. The outer surface blocks visible light. It doesn't see visible light. It sees infrared, and when it absorbs infrared, it expands. It presses against nerves here, and then that's how the beetle detects infrared. From that distance, they cannot smell or see or anything. Another creature that detects infrared is a family, actually, of insects, and these are blood-sucking insects. And what they do, they detect infrared, they detect animals, and not only that, apparently they have infrared detectors somewhere here. You see, they have like antennas sticking from their heads, and they have infrared detectors probably at the ends of it has not been established truly, but apparently there are infrared detectors, and they detect infrared radiation from blood vessels under the skin, and that they suck the blood under the skin. And there are many, many families of snakes. Snakes lived under the ground for millions of years. And when they lived under the ground, in order to detect prey, they had to detect infrared emitted from rats or or some other small animals. So they developed infrared sensors, but actually imaging devices. They can see a full picture in total darkness of, for example, a rat or a mouse under the ground. When the snakes reappeared above the ground, some of them kept two pairs of eyes, one pair for daylight and one pair for night or whatever, and then they have like a computer in their brain with and/or. So at night they operate one set of eyes, infrared eyes, daytime visible eyes, and in twilight or in the morning they operate both sets of eyes to get their prey. And the detectivity, the ability to detect infrared is fairly good. They can detect a mouse in total darkness from roughly 1 meter. And these are some of the snakes. This is a python, you see, and the arrows show the infrared cameras on the nose of the snake. And this is another python, and you see here the snakes. They have also infrared cameras. Some of the snakes have infrared detection system inside the mouth, so that when they open the mouth to catch a mouse, they can see infrared through the mouse. And this is, you see here, two pairs of eyes, one for the visible and one for the infrared. And how does the infrared camera work? They have a very, very thin membrane. Now, the eye is like a pinhole camera, so they don't need a lens. And on that very thin membrane, there is an image of an animal. In the membrane, there are ends of nerves, and the thermal insulation is very good. It's in air, and that's how the thin layer can get a full image in total darkness. And last but not least is a family of bats, vampire bats, that live in South America. These are small creatures, like 10 inches or so, the wingspan, and they feed only on blood. So they need to detect large animals in the forest. And then when they detect an animal, they jump on the animal, normally on the hind legs, and they detect blood vessels under the skin, and they suck about 25 or 30 grams of blood. One interesting thing is that when they suck the blood, they want to prevent coagulation. So from their teeth, there is a protein that they use to prevent coagulation. And in the news a few weeks ago, they said that this protein may break blood clots in the brain after a stroke. So now there are clinical studies that make use of the protein that these creatures have. And this is a photograph of this creature. As you see, these are the teeth. And the amazing thing, apparently here there are 3 infrared cameras. So the creature moves the nose in order to get thermal image in full darkness. Now, these were infrared detection in nature. Now, what are we doing? We are using infrared radiation between 3 and 30 micron for various applications. For thermal emission, like measuring temperature. There are many, many lasers that operate in the mid-IR. And in spectroscopy, there are many molecules that vibrate or rotate. Each vibration or rotation gives rise to absorption in the infrared. So there is spectroscopy in the infrared. And there is a new thing called infrared microscopy in the infrared. So in all these applications, it would be very interesting to have fibers that are transparent in the infrared. Let me remind those of you who don't know about fibers. A fiber is a thin thread of the electric material, and light is reflected back and forth inside the electric material if the electric material is immersed in air. Or you can have 2 materials, like a rod in a tube. The inner rod has a higher index of refraction, and the light makes a zigzag path through the inner core of the fiber. Most of the fibers that are being used today are made of silica or of some polymers like lucite, perspex, and they are totally opaque in the infrared. And if you're trying to make fibers that will operate in the infrared, you have to consider what are the optical properties of materials that are transparent in the infrared. So in many, many materials, there is something called the V-curve. V-curve means that the material is transparent in some region, And there are two areas. On the left-hand side, there is Rayleigh scattering. On the right-hand side, there is multiphonon absorption. And the end result is a V-shaped. This is for a material like silica, where the absorption is, the minimum absorption is around 1 micron. But in the infrared here, the absorption is already high. So you cannot use silica or lucite or whatever for infrared transmission. So there are other materials, not silica, not polymers. These are some of the materials that can be used in the infrared. These are glasses, different glasses, which are transparent. Silica, as you see on the left-hand side, is not transparent. And one of the materials that is good for the mid-IR is silver halides. Silver halides are crystals that have been known for more than 100 years, and they are being used in photography, for example, and they are highly transparent. So this is the transmission of silver halide. You see between the visible, half a micron or so, and 25 or 30 micron. So a crystal of silver halide is highly transparent in the mid-IR. Therefore, we selected silver halides as the material that we will make fibers from. And we started many, many years ago. We purchased the components from Kodak or from other vendors. We make a powder, very, very pure powder of silver halide. We melt the powder, slowly cool it, and get large crystals. The crystals are composed of silver chlorobromide, actually. It's an alloy. And we can determine the composition by various ratios of silver chloride and silver bromide. And you see here, this is a compound that consists of more chlorine, and this consists of more bromine. All these compounds are highly transparent in the mid-IR. Now, from the crystals, we extrude fibers. We push the crystal through a small die, small hole, and this is a soft material like Clad, and if you push it, you get a nice and long fiber. So this is a cross-section of the crystals. This consists of more chlorine, this more bromine, and these are some of the fibers that are extruded from these crystals. And since the composition can vary, the index of refraction of the compounds that contain more chlorine is lower. If you have a crystal of silver chloride, it has a lower index of refraction than silver bromide. Therefore, you can make fibers with core and cladding. The core, the inner part, consists of more bromine, the outer part of more chlorine. So you can have long fibers which are highly transparent in the infrared. This shows the transparency, and the transparency is worse than in a crystal. We still don't know why, but these fibers are transparent roughly between 5 micron and 17 or 18 micrometers, and these are among the best optical fibers for this spectral region that anyone has. Now, these are some of the properties. I'll not bother you with the details, but we can make fibers that are core and clad, rod in a tube, or just unclad, just the rod, and length up to 15 or 20 meters. You can bend them around your fingers, nothing happens. And most importantly is that they are not soluble in water. They are not toxic. You can eat it, nothing will happen to you. And they don't darken under light, unlike photographic material. What are the applications? So I'll go one by one through the application. One important application is carbon dioxide power delivery. Carbon dioxide is a laser that emits at around 10.6 microns, and this is the laser that is probably the most important laser for surgical applications. There are many companies in Israel and abroad that make this laser. The radiation of the laser is highly absorbed by water, and if you focus the light onto tissue, you vaporize the tissue, and then you can cut or drill holes. So this is laser surgery. And with the carbon dioxide laser, if you want to do operations inside the body, then you have to send it through a material that is transparent to 10.6 microns. And silver halide is one of the best materials. And we can transmit tens of watts continuously, or pulses of 10 of joules, and this is a relatively good performance. So this is power transmission. Another application of the same fibers is for temperature measurement. All of you know the black body radiation. So this is the radiation emitted from a black body. And as you can see that near room temperature, most of the radiation is around 10 micrometers. So if you want to measure the temperature of a body through a fiber, the fiber has to transmit between 5 or so and 15 micron. And there are very, very few fibers that can do it. Silver halide fibers do it, and therefore you can construct a fiber that will transmit radiation. This was for a black body. For a real body, there is a problem with the emissivity. And I'm not going to detail. One can also solve the problem for emissivity. In the case of soft materials, soft tissues, which consist mostly of water, the emissivity is 1, and therefore you can replace epsilon by 1, and you can measure the temperature like in a black body. So this is the system that we have developed over the years, an infrared detector and a fiber, and if you place the fiber near a warm body, specifically near room temperature, you can detect the radiation emitted from the body and determine the temperature of this surface. The resolution in temperature is very good, 0.1 degrees centigrade, and in space, it's about 1 millimeter, the diameter of the fiber. Now, combining the two things, I can transmit light or energy through a fiber, and I can measure temperature through the same fiber. And I can combine the two things for a thing that is called laser bonding of tissues. And the idea is the following. If one makes a cut in tissue and approximate the ends of the cuts and hit it gently with a laser, for some reason that is not well understood, the ends of the cut will bond together. And borrowing from metallurgy, you can simply take a cut and do it, or you can approximate the ends of the cut and spread on it some biological material, like, for example, albumin, and get a nice bonding. So in both cases, the problem has been, or the laser bonding of tissues has been known for many, many years. But it has not been approved by the authorities in the United States, and there is no wide clinical study of laser bonding. And we think that the reason is that you need to do temperature control. Not everyone agrees. So many years ago, we decided that we are going to study this problem. And why do you need it? Because if, God forbid, you have a cut or an operation, physicians know how to use sutures or clips or glues to bond it. And this is very simple, relatively inexpensive, and so on. But the problem is, if you introduce sutures or glues or stitches, you introduce a foreign body into your body, and your body rejects it. So instead, what we are offering is a method that does not introduce another body, a foreign body to our body. We also offer something that will be hopefully watertight, unlike sutures, that you have a suture every millimeter or so, and it will probably be simpler to do it. So we built a system that looks like that, a carbon dioxide laser, commonly used. Through a fiber, you send radiation to a spot on the body of here an animal. The spot emits infrared radiation according to the black body radiation. You pick it up with a second fiber, measure the temperature, and you have a feedback loop that controls the temperature. And we found in many types of tissues that the best conditions are to have bonding at around 65 degrees centigrade and around 10 seconds. And we started a series of experiments going, that's the law in Israel and in other countries. You have to start from very small animal, from mice, and ending with farm pigs. The size of the pig is about 75 or 85 kilograms. And on the backs of the pigs, the surgeons made cuts. These cuts were laser bonded, and these are sutured. And as you see, after 7 days, the laser bonded cuts look better. And because of that, we got permission to do clinical studies. And in the month of April, last month, we did experiments in the Ha'emek Medical Center on 6 patients. We got permission to do 10 patients. So we got 6 patients, 5 women, that's statistically 5 women and 1 man. The procedure is called laparoscopy. Laparoscopy is when you have to remove, for example, the gallbladder in patients. Then the physician drills 4 holes in the body. Through one of the holes, the physician inserts an endoscope to see inside the body. Through another one, they introduce pressurized gas to inflate the belly, and through 2 other holes, they insert all kinds of tools for cutting or removing or whatever. At the end of the procedure, there are 4 holes in the belly. And today, they use sutures. And the sutures mean that they are nice scars. So we got permission to do 2 of the holes with a laser and 2 with sutures. And you see here the patient 1 and patient 2. On the left-hand side, you see the sutures. On the right-hand side, you see the laser solder. So first of all, in all the 6 patients, the system worked very well. The question is whether the scar will look better, if it will heal better, hopefully if there is going to be no scar. So this is after 1 month after operation. We have to probably wait 3 or 4 months. The photographer did not do such a good job because they took it from the top. But what apparently happens is that here the sutures protrude from the surface like a regular scar. And here this is flat. And the patients also, when they feel it, they see that it looks better to them. So we'll know in 2 months, we'll know if the procedure is indeed better. And so this is one of the first clinical experiments in the world on this type of procedure, and we hope that it will continue. We work now with many, many groups of surgeons, skin, blood vessels, in ophthalmology, on cornea, and so on. And in my opinion, the most important thing is endoscopic surgery. Physicians do use endoscopes, and it's very easy for them to cut parts of tissue or anything inside the body. But to suture it through an endoscope, it's very difficult. They use very long needles, like when you sew at home. And they hold the needle here, and they suture it there. And it's very difficult. Very few people in Israel are skilled in that technology. But if you are using the system that we offer with the 2 fibers, it will probably be easier to do. We did experiments on pigs where cuts were made in the kidneys, and there were sutures, they were laser bonded with the system that I discussed earlier, and that seems to be working very, very well. So this is the topic of laser bonding of tissues. And from that, I'd like to switch gear and move to another totally different thing, and that's evanescent wave spectroscopy. And that's a novel way for measuring absorption spectra of material. This is not a new idea. Already, Mr. Newton, in his book, he took a prism and he observed total internal reflection. And when the prism touched honey or oil or some other liquids, he observed a change in the reflection. So this is the property of total internal reflection. And today we are talking about the following thing. If you take, for example, glass and air, and you send light from glass to air, you may observe total internal reflection. If you look at the wave picture, you see here that in the air you have evanescent field that decays. And there is something called D, and that's the penetration depth. And the penetration depth depends on the wavelength of the light, on the indices of reflection, N1 and N2, and on the angle at which the light is impinges on the surface between glass and air. Now, if it's not glass and air, but say glass and honey or some other material, then you see this is the incident beam, this is the reflected beam, this is a representation of the evanescent field, and if you want to solve the equations, you have to replace N1 by an imaginary value, and you get that IR is smaller than I incident. The reflected light has a smaller intensity than the incident. This is only at a wavelength where this material absorbs light. And therefore, this can serve as a basis for spectroscopy that has been known for generations. Instead of doing transmission spectroscopy, where you send light through a thin sample, you put a sample on, for example, a prism, you send light, and you change the wavelength. So for every wavelength that there is absorption, you see change in the transmission. So that you get practically the same results here and here. This has been developed to what is called ATR spectroscopy, attenuated total reflection spectroscopy, or evanescent wave spectroscopy. So instead of a prism, you have a waveguide. This is the light goes up and down, and every time the light meets the sample at the wavelength that sample absorbs, I transmitted is smaller than I incident. So you can measure the spectrum of a sample just by touching it. So the advantage is that you don't have to prepare a very, very thin sample, but you can simply touch the sample with an ATR element, a prism or a waveguide, and measure its absorption. And you can then replace the waveguide with a fiber. Since we know how to make fibers, the fiber can also serve as an ATR element, or attenuated total reflection element. So you send beam from one side to another, and you measure the absorption of a sample in contact with a fiber. And we did it in two ways. We took a regular spectrometer that consists of a tunable source and a detector, and placed a fiber inside. So the light made a zigzag path, like you saw earlier, and if the sample touches the fiber, we can measure the absorption spectrum of the sample. And the source can be something called FTIR, Fourier Transform Infrared Spectrometer, a regular spectrometer, or a laser. Or alternatively, you take the same spectrometer, but from the spectrometer, you can pull out very, very long fibers and do the measurement somewhere remote from the spectrometer, the distance of 10 or 15 or 100 meters from the spectrometer. So you can touch a sample away from the spectrometer and measure its absorption. So we use this system for a variety of applications. So first of all, in all spectroscopic measurements, you need to increase the sensitivity. So one way of increasing the sensitivity is this is a soft material. If we press it at its center, then we get at the center, as you see here, many, many more reflections, and also the angle changes. And the penetration depth, as I showed earlier, depends on the angle. So it turns out that if you press the central part to a thickness D, then the sensitivity is almost linearly dependent, like 1/D. So this is what we have. This is a central part of a spectrometer. This is a fiber that is pressed at its center. And if you let the sample touch the fiber, you can measure the absorption of the sample. And I give you a few examples. The first is water. So we studied the phase transition of ice and water. We placed ice, let it the ice was at a low temperature. Gradually, the temperature increased to room temperature, and we followed the absorption spectrum throughout the heating of the ice to water. So, and the advantage is that you can make many, many measurements throughout the heating. So water has different vibrations, as you see, symmetric, asymmetric, bending, librations, and so on. Each of them gives a different absorption. And these are the ice, for example, and the water. You see ice is blue and water is red. And we follow the stretch and the bend and the libration of water. And I'll not go again into detail, but if you do it carefully, we found there is something called the isosbestic point, and we found a new isosbestic point of water and ice, because regular measurements on water are very difficult. Water absorbs strongly in the infrared, so if you want to do the same measurement in a regular spectroscopy, you have to prepare a thin sample of water, like 10 micron in thickness, and follow it, and that's very difficult. With our measurement, it's very, very simple. And if you take just a stretching part that I showed, we decompose it into 5 components. Some of them increased in the range between -4 and 4 degrees centigrade, some decreased, and this helped us develop a theoretical model for the phase transition, and this model helped us to explain some of the well-known anomalies of water, such as density and the heat capacity and so on. So this is one area where it's very, very easy to do measurement with this system. And another thing that is also very easy with this method, very difficult otherwise, is to measure the diffusion of water into something. And something that we chose was Teflon. So the idea is to measure the spectrum of water inside Teflon. And why is it of interest? Because there are many, many papers dealing with that. Many people are interested in water in hydrophobic polymers like Teflon. And that has also some relevance to biology and other fields of research. So what we did, we took fiber, coated it with Teflon. Teflon does not absorb much in the infrared, and we placed it in water. The water molecules, the red ones, gradually diffuse into the fiber, into the Teflon, and then you observe that's the evanescent field. So gradually you see the absorption of water inside the Teflon. And you can follow it, and these are some of the results that we got. This is the bending mode, and this is the stretching mode of water. And you see that following it in time. And we found if you plot it as a square root of time, we found how the bending mode on one side and the stretching mode on the other side give rise to an almost linear curve. And this is another linear curve. And again, we developed a full theoretical model for the explanation. And we think that water forms clusters. The inner part of the cluster is strongly hydrogen bonded. The outer part is weakly hydrogen bonded. And the two types of molecules give rise to the two lines that you saw earlier. So we can use this method for the study of diffusion. Another thing that we can do is to use it in biology and medicine. In biology of medicine, people are interested in infrared spectroscopy because many, many molecules reflect the state of biological molecules. For example, if they are healthy or unhealthy. So as an example, clinical chemistry. I mean, right now, in clinical chemistry, if you want to analyze blood or urine or whatever, you take it to a laboratory and you use reagents and so on. If you use the spectroscopy, you don't have to use that. And I give you one example, urinary stones. Many people have urinary stones, and if you remove the stones, there is a recurrence. I mean, the stones come back. And physicians would like to know what is the consistency of the stones to help tell the patient eat or don't eat or drink or whatever, what you should eat and drink. Today, the method that are being used to remove the stone are either shockwave lithotripsy. You place something on the body of the patient and then send a shockwaves that shatters the stones, or you do it endoscopically. And the end result is the stone is shattered. There is a powder with very, very small particles that the patient urinate. And the question, how do you analyze the small particles? Obviously, you can do mass spectroscopy or X-ray or whatever, but these are time-consuming and expensive, and you need a large quantity of this powder. Alternatively, you can take the same system that I described, put a very, very one or two pieces of the shattered stone, weight less than 0.2 milligram, and you can do the analysis of the urinary stone. This shows you some of the minerals that, if you study urinary stones, these are some of the minerals. So you can do analysis very rapidly and very inexpensively. Another thing that one can do is pathology, not to replace the pathology, but give them another tool that may help them. And for example, there are many, many diseases where the pathology possibly is reflected in infrared transmission. And I'll give one example. This is when you measure healthy skin. You get complex spectrum, and each of the peaks can be identified. So we did the same thing with a fiber. So this was done in Ichilov, in the medical center not far from here. This is a spectrometer, and this is a fiber. You cannot see it very well, but this is a member of my group, and this is a physician in Ichilov hospital, and she touches a fiber with her finger, and you can measure in 10 seconds the absorption of the skin on her finger. And we started last year to do analysis of patients, and of all these patients, only one of the patients in Ichilov had melanoma, skin cancer, and as all of you know, it's very, very important to have early detection of melanoma. The reason is if melanoma is detected when its thickness is less than 0.3 millimeter and it's removed, the patient will survive. If it's more than 3 millimeter, the patient will die. So the analysis right now depends only on one thing, on the eyes of the surgeon. But the question is whether infrared can help. We don't know. But on that one patient, you see A is the normal skin. There was a lesion, a woman had a lesion, cancer, and away from the lesion, the measurement was done, and this is the black line. B is the periphery of the lesion, and C, the center of the region. So we see some changes, but we don't know yet if it's sufficient. So now, next week, we are going to try a large series of experiments, collaboration of 2 hospitals, Ichilov and Sheba Hospital in Tel Aviv, and we'll have patients who have melanoma, and we'll see if we can define some characteristic absorption spectrum of cancer, which will enable us to do early diagnostics of cancer. And there are other applications of the same method, and I'll describe only one of them, and that's the water security. And that's not only the question of Al-Qaeda, but in Germany, in November of 2005, some farmer decided that the German government mistreated him, so he poured poison into a lake, Lake Constance. And the question is, how do you detect such poisonous material? And again, water has characteristic absorption spectrum. Each of the poisons that we use has a characteristic spectrum. These are 3 of the pesticides that are commonly used by farmers. And as you see here, these are concentrations between 0.5 and 30 parts per million. We can detect half of a part per million, or probably 0.1. And you see each of the poisons has a different characteristic spectrum. So we think that we can develop a system for online monitoring of poisons in water, and that relates to environmental protection, but also, God forbid, in the case where Al-Qaeda or someone else will try to pour water in to our Yarkon River or to places like that. And just to mention, the concentration that is needed is 0.1 or 1 part per million. 1 part per million will not kill people here, but will kill a young, an old person who is sick, or a baby that is 2-3 days old. So it's very important to detect 1 part per million, and to the best of my knowledge, no one in the world has a system for online monitoring of toxic materials in water. And maybe I'll skip that, and I'll move to the other part of the talk. And this is a part that deals with single mode fibers. And what are single mode fibers? I'll describe in a second. But these are fibers that have many, many applications. And I'll describe only one of their applications, and that's an application in astronomy. And in astronomy, there are 2 competing bodies. One is NASA in the United States, and the European Space Agency in Europe. Both bodies are trying to find habitable Earth-like planets not so far from us. And the idea is that they are looking for pairs of body, like a sun-like object and an Earth-like object. And the idea is that the Earth-like object should not be too far from the sun-like object, because otherwise they will freeze, and not too close because everything will evaporate. And the Earth-like object should have a sufficient mass so that it will have an atmosphere. And so there are indirect ways of finding such planets, but many people are trying to find it directly. And how to find it directly? By looking at the atmosphere. And if life is like our life, then they should look for water or carbon dioxide or ozone or whatever. So the project, this all stemmed from the project of NASA and the European Space Agency. The project of NASA was called Origin of Life. Then they switched names and so on. So now NASA calls it Terrestrial Planet Finder, PPF. And the Europeans call it Darwin. So they're looking for these planets. And one of the important methods that will be used is nulling interferometry. And I just want to mention that on the 24th of April, I guess that most of you saw the news all over the world, all the newspapers, all the television stations advertised the fact that in something called the ESO, the European Southern Observatory in Chile, decided that they found Earth-like planet, which is not like the one, the Sun-like and the Earth-like object, but still that shows the interest of people in trying to find life outside our Earth. So what is nulling interferometry? If you have the Sun and the Earth, the Sun emits enormous amount of light. And how do you detect it? So the idea is to have an interferometer that will look at the Sun, and you adjust the interferometer that it will null or it will highly reduce the radiation from the Sun. And if the planet is at some angle from the star, the interferometer will not null the radiation from the star, and maybe you can get it. And this is very, very simplified version of what they do. They have a number of mirrors, and they're going to send it to space. NASA at least say that they are going to send it in 2014, an interferometer that will sort of look for the radiation from that planet with nulling of the star. And why infrared? Because NASA did calculations, and they saw this is the Sun, and this is the Earth, and this is the wavelength. In the visible, the ratio of the radiation emitted from the Sun to the radiation emitted from the Earth is 10 to the 10th. In the infrared, it's only 10 to the 6th. Here it says 10 to the 7th, but they say roughly 10 to the 6th. And also in the infrared, they have all the characteristic absorption spectra, so they can distinguish CO2 or ozone or water. So they're trying to build an interferometer that will look in the infrared. So this is the project both of NASA and of the Europeans. And ideally it's okay, but if you look at space, there are problems. The dust and the telescope and so on. And as a result, they think that the wave pattern will be completely destroyed, and they cannot do it. So their idea, both groups, both institutions think that they need somehow to solve the problems, and there are two ways of doing it. One is called spatial filtering, send the radiation through a hole or through a fiber. And again, I'll not go into detail, but I'll explain that both the Europeans and the Americans are looking for something called single mode fiber. And what is single mode fiber? This is the fiber that I described earlier. This is the core, and this is the cladding. The core has a higher index of refraction. And that's why if you plot the index of refraction, this is high and this is lower. Now, if you do the analysis of optical fibers, there are many, many modes, like in other fields of physics. There are many, many modes that can propagate. If you think about the zigzag path, there are many, many types of zigzag path that can propagate through a fiber. And the total number of modes is given by this number that is called V number. Depends on the radius of the fiber and the indices of refraction and the wavelength. And so this is the V number, this is the number of modes, and if the V number is smaller than 2.4, there is only one mode, and that mode looks like a Gaussian. So if you develop a fiber that looks like that, it will be a single mode, and the idea of communication networks, the optical fibers for communication, also makes use of single mode fibers. And so this is the idea, is that you have the planet, and you focus the beam onto a fiber. The beam will not look nice, not a Gaussian or whatever. There are many, many, it's distorted. And if you focus into a fiber, then in the fiber, all these noises will disappear, and only at the end of the fiber, you will see a nice Gaussian. So a single mode fiber is called a modal filter that will get rid of all the other imperfections and get one mode. And the troublesome thing is that they want to get rid of all these things by a factor of 10 to the 6. just to get what they need. And it looks like a science fiction, but it may not be a science fiction. But this is what they're looking for. So that's the idea of the Europeans or the Americans, that they have several telescopes, and each of the telescopes will have a single fiber at its arm to clean the beam, and then they can do the interferometry here. And what happened is that they are looking for the spectral range roughly between 6 and 18 micron. Why? Because water and carbon dioxide have strong absorption peaks around 6 and around 17, so they need that spectral range. And what I mentioned, that the V number that I mentioned earlier depends on the radius and on the indices of refraction. So you need a small a and a very, very small difference between N1 and N2. And they approach us because we are one of the very, very few groups in the world that can make such fibers. And we did some estimate for NASA, for JPL, and it turns out that to get a single mode operation, the difference between the indices of refraction should be very, very small. And also the core diameter should be very, very small. Now the index of refraction depends on the composition. So that means that also the composition, this is silver chlorobromide, so the core and the clad should have almost the same composition. So the indices of the refraction will be almost the same. So we started working on that roughly 4 years ago. So first of all, we determined the index of refraction of the composition, and we found that we need very, very precise control of the composition. That was very, very difficult, took us years. We had to grow crystals where the uniformity throughout a large crystal is of the order of 1%. That took years, and then we had to grow very, very small core. That was also very, very difficult, but we managed to do it. And just to show you, we sent a CO2 laser beam into such a fiber with a very small core and a very small difference between the indices of refraction. And we measured it, and we got at the output a Gaussian. We made many, many measurements that proved that this is single mode fiber, possibly the only group that has such single mode fibers. And these were tested in a test bed at JPL near Pasadena, and they also think that this is a single mode fiber. That's another proof. To imitate a star, we took a CO2 laser and we took a series of silicon windows which destroyed the shape. You see, this is the laser itself. It's a Gaussian. After the silicon windows, this is a horrible shape, and you send it through a fiber and you get again a Gaussian. So this imitates what will happen, hopefully, in space. And now I'll switch gear to some other thing, and this is called periodic structures. Now, in 1873, Lord Rayleigh wrote actually a number of papers on periodic structures, and as a result of this, people use the anti-reflective coating that you may have in your cameras or optical equipment. And then in 1973, Jablonovich and then other people sort of extended the idea to 2 dimensions and then to 3 dimensions, and they use something called photonic bender structure. Photonic bender is like a crystal. In a crystal, the electrons have a band gap, and in this structure, the photons have a band gap. They cannot propagate. They are reflected. Or photonic crystal fibers. And this is not the only, again, nature is also very, very clever. And in nature, there are many stones and also animals make use of periodic structures to get colors. So this is not a paint or whatever. It's not a color. It's just, I mean, it is a color, but it's generated by periodic structure. So these are some of the examples of the periodic structures in nature. And what people started doing over the last maybe 10 or 15 years is to develop fibers that contains periodic structures. These are some of the fibers, some of them called photonic band gap structures, and some are total internal reflection or photonic crystal fibers. And this is an example of such a fiber. Instead of a core and a clad, there is a core here at the center, and instead of a clad, you can see here many holes which contain air. Air has a low index of refraction, so therefore the layer outside has an effective index of refraction that is slightly lower. So you have here a core and a clad, but the clad is called holey, H-O-L-E-Y. This is a fiber with holes. So this is one of the examples you see here. That's a core and the air holes. And this is a structure that transmits, and it may be very useful for optical communication. Very few people have the same thing in the mid-IR. So we develop periodic structures in the mid-IR. This is a cross-section of the thing that is called preform, before you extrude the fiber. So instead of air, we have two types of crystal. Crystal, you see here, this is the central part that contains less chlorine. It has a higher index of refraction. And the outer, what you see here, these are optical fibers made of silver chlorobromide with a high concentration of chlorine, lower index of refraction. So we have here two layers, or one core and a layer outside with a lower index of refraction. And when you press it, you get a fiber, and the fiber is not so good yet, but if you send CO2 laser through one side, you transmit through the core radiation. And we are continuing with this work because in principle this fiber has good properties, as you'll see in a minute. This is another type of fiber that we develop. Instead of holes, we have here core, and on the outer part of the fiber we have a series of like lines made of different materials, so the index of refraction on the outside is smaller than the index of refraction of the core. And just to show, this in principle should work better than a regular fiber. First of all, you can have a single mode fiber with a much larger core, and that will be vital for the NASA mission or the European Space Agency mission. Instead of a core which is typically 35 or 40 micron, maybe we can have a core of more than 100. And secondly, the calculations show that the spectral range can be theoretically unlimited, but at least it will go to 20 or 22 microns. Again, it's vital for the NASA project. So this is what we made, and that's just to show that we got single mode operation in this periodic structure. And now I'll switch gear to a totally different area, and this is called fiber lasers. Every laser consists of some medium, which is an amplifier, and two mirrors. And in principle, that medium can be a fiber, a doped fiber, a fiber that contains some dopants. And over the last maybe 50 years, people tried to take either crystals or fibers and dope them with dopants. A typical dopant is a rare earth ion. And people made lasers like neodymium YAG, which is a crystal, or neodymium glass, which is a glass. And from the glass, they made fibers, and they used these fibers mostly for optical communication. But all these fibers are highly opaque in the infrared. And the question is, can you make fibers that are transparent in the infrared and make from them lasers? And why would you need such a laser? And again, our friends in Al-Qaeda, except for poisoning our water, they may do other things that are also dangerous. And they have roughly 20,000 shoulder launch missiles. This is a shoulder launch missile, and this is a farmer. The farmer has to know one thing, to point roughly at the direction of a civilian aeroplane and push one button. So even Al-Qaeda people can do it. And the missile is very primitive, and it detects one thing. It's the tailpipe of the aeroplane. The tailpipe, the temperature is around 1,000 degrees. Therefore, it emits roughly 3 or 4 micron radiation. So the question, how to fool the missile. So one thing that all the civilian aeroplanes will have to have is a radar system that will detect the incoming missile. and then they have to defend themselves within roughly 2 seconds. And how to defend themselves? And the idea is that they'll send a laser beam at 3 or 4 micrometers towards the incoming missile. They'll saturate the detectors, blind it, and the detector will not see the aeroplane, and it will miss the aeroplane. So the radar systems are not difficult. The laser itself is difficult, and many, many groups are trying to develop such lasers. And the laser has to be portable, and it's advisable that the laser itself will be a fiber. Why? Because suppose that we are in an aeroplane, and the fiber sticks out of the top of the aeroplane. If you detect a missile, the fiber will be aimed at the incoming missile, and then you fire a laser shot and maybe fool the missile. So we have been, we thought that since our crystals are transparent in the mid-IR, that we'll try to dope them with rare earth ions. And we started with neodymium. So in the field of laser development, people measure absorption, luminescence, do calculations, and then try to build the laser. So you have to start with the absorption measurements in order to establish a set of energy levels and try to calculate which levels can then give rise to lasing. So this is the absorption that was measured in a silver bromide crystal. And as you see here, there are many, many lines. Then we measured the luminescence at room temperature. You illuminate the crystal with some UV or blue or whatever near-infrared radiation. And we observed strong luminescence between 4.5 and almost 6 micron. And this is the set of energy levels. And this is the transition that we think may help us form a laser that will possibly serve for countermeasures against shoulder-launched missile. These are some of the ions that we tested, and some of them have a high quantum efficiency, and it seems that we are on the right track. So we are working on these fibers also as sources for lasers. And the final thing that I wanted to show is a new type of microscope called scanning near-field infrared microscope. And this is a microscope that can give you probably a resolution that is smaller than the wavelength. Now, why do you need such a high resolution? There are 2 fields of research where it's important. One is in biology. If you take a typical cell, suppose that the size of the cell is 10 micrometer. In the cell there is a nucleus and other subcellular structures. The size of the nucleus is of the order of 2 micron. People who did microscopy with standard microscopes found that indeed in the region of 5 to 10 micrometers they see something, but the something was measured on a large number of cells. And the wavelength, as you see, is much larger than the size of the nucleus. So how do you do spectroscopy of the nucleus? The same goes for integrated circuits, where they have small devices, and the size of the device is now smaller than a micron. And suppose that you want to measure the temperature of the junction of a transistor on an integrated circuit. How do you do it? Because it's smaller than the wavelength. So this problem was understood by E.H. Sinch, who in 1928 wrote a paper, and then he had discussions with Einstein, and then in 1932 he wrote another paper. And the problem is to solve the Abbe principle. The Abbe principle says that basically the resolution is the wavelength. You cannot see things that are much smaller than the wavelength. So Sinch offered a solution, which I'll explain in a second. And then the famous physicist Hans Bethe did a complete set of calculations in 1942. And finally, in 1944, Aaron Lewis in Jerusalem managed, pardon? 1984, Aaron Lewis in Jerusalem built such a system, and he gave here a colloquium a few years ago describing it. And Paul did the same thing, roughly the same time. So what is the idea? The idea is the following. Suppose that you have a screen of metal with a small aperture, A. and A is smaller than a wavelength. Then you send a beam of wavelength lambda onto the screen, and what you have here is evanescent field, like the evanescent field that I described earlier. The evanescent field decays rapidly, and if you put a sample far away from the screen, you see nothing. And according to the calculations of Bethe, the ratio is 10 to the 12 of the intensity. So you see nothing. But if you bring a sample very, very close to the pinhole in the screen, then there is tunneling, much like in quantum mechanics. So the light tunnels, and then it becomes again a propagating beam. So what you see here is you have a propagating beam, evanescent field, and then another propagating beam that can be monitored by a detector. So the idea of Singe and then the calculations of Hans Bethe show that the radiation now has a relatively high intensity, and therefore you can do the following. You see, you move the pin on a sample, and you get light, no light, light, no light. And the resolution is determined by the size of the pinhole, not by the wavelength. This is the idea. Now, Aaron Lewis tried to build it, but it's difficult to build it with a pinhole because the pinhole or the screen is large. So Lewis decided to do it with an optical fiber. So what he did, he took an optical fiber, he tapered it by pulling or by etching, and he coated the sides with metal. So here is an aperture smaller than the wavelength. You bring it very, very close to a sample, and as you scan it, you see light, no light, light, no light, and you can see sub-wavelength features, almost lambda over 100. You can see very, very small features that you cannot see with regular microscopy. And we wanted to extend the same idea to the mid-IR and use the same type of fibers because, as I mentioned, regular standard microscopes, commercial microscopes, have a resolution of maybe 20 or 30 micron. They cannot look at individual biological cells. So we try to build something that is called SNIM, Scanning Near Field Infrared Microscope. So we first of all took our fibers and put them in an etching solution and generated a tip. The size at the tip, the diameter of the opening is about 1 micron, much smaller than the wavelength. And as you see, we coated the fiber with metal, left a very, very small aperture, and we used it as to build a microscope, which took, again, several years. But the idea is that you can do the same thing as Professor Lewis did. You can scan an image and scan an object and get an image with a very, very high resolution. And if you do it with different wavelength, you can do what is called spectral imaging. At each point, you can measure the absorption spectrum of that point. So this is what we built. And recently, we got it to operate in this system is in air, but if you want to do it on cells, on biological cells, there is another complication that you have to do it on underwater. So we managed to do this type of measurement underwater. So we have a fiber. We put not cells, but we put some plastic beads on an infrared fiber. So when you scan with the tip the beads, you can see here that there is a bead, here there is a fiber, here there is a bead, here is a fiber. So when you scan, you can see that there is a bead or no bead. So this is what we got. This already works with beads whose size is roughly 1/3 of wavelength. So this is a first step, and the next step we'll put living biological cells here and try to do imaging, specular imaging of biological cells. And there are many people who are interested in the spectrum of biological cells. For example, people who are trying to study cancer or Alzheimer's disease or mad cow disease want to see spectrum of one cell, not an array of cells. So this is just to show you the results that we got. These are the beads that you see on the side. These are plastic beads. That's a regular microscopic picture. with a wavelength of half a micron, visible light. That's not difficult because the wavelength is 1/10 of the bead size. These are the images that we got for the first time using a CO2 laser, 10 micron. You see the size of the bead is in this case 5 micron. So the bead size is half of a wavelength. And this you can do also topography. So we think that we are very close to making measurements on individual biological cells, and by the same system we can also measure electronic circuits. So in summary, I took you through a tour of what optical fibers can do. They can do power transmission for laser surgery. They can detect IR emitted in a remote location for thermometry or thermal imaging. They can do diagnostics of various things in biology, environmental protection, industry, and so on. They can hopefully laser and serve for either spectroscopy or for, again, homeland security. And hopefully they'll also serve as a basis for a new type of microscope. So this work was done in collaboration with many, many people. Some of them are mentioned here. So they did the hard work, and I gave the talk. So I thank you.
We still have time for some questions, please.
Everything is understood.
So, David.
Could you understand what is the advantage of having fibers themselves create lasing when you want to use it for things like homeland security? You have a regular laser, but just use a fiber to get the right direction.
There are two, the way the Americans work, I mean, there are different agencies that give money, not to Israel, unfortunately, but give money to the development of lasers. And they have, the thing that they need is a portable laser. You cannot, and I attended many meetings, and many companies like Grumman and all these large manufacturers of missiles and so on show a portable laser the size of this table. So this is slightly less portable than what we have in mind. So their idea is to have something like that, a very small laser and a fiber sticking from the laser, or alternatively a laser that will be a fiber itself. In both cases, you need a small laser. So one option that we have is to take one of our crystals, dope it and get a laser, transmit the radiation of the laser through a fiber, or to have the fiber laser. And I don't know which is better, and obviously they don't tell us exactly the system requirements, but in the what they call request for proposal, RFP, they specifically are looking for fiber lasers. And so I cannot tell you exactly why, but we are working on both projects.
No, please.
Does your group have any policy on patent protection? On the small chance that one of these ideas might eventually make something?
The problem is as follows. I mean, we have the agency that is responsible for patents at Tel Aviv University is Ramot. And if you submit a patent in Israel, it's very, very inexpensive. If you submit it in the United States, it's very, very expensive. Not very expensive, but it's tens of thousands of dollars. So in most cases, I and many other people, when we submit a patent idea, it's normally rejected. So I cannot. So that's short-sighted, in my opinion. That's a short-sightedness of Tel Aviv University. We, in some of the things, we submitted patents. In others, the patents were rejected by Tel Aviv University.
Any more questions? Can you explain very qualitatively why, when you had these two indices of refraction so close, there was a single mode? I mean, there was a, just to remind us, some elementary thing. I think if the indexes of refraction are almost the same, there is not much of a reflection, no? So they keep going through the...
No, it's the...
I'm talking about the single mode.
No, I understand. I mean, it's a combination of two things: the small diameter, yes, and the small difference in the indices. So if you plot a fiber, and even if you use the very, very simple model of a zigzag path,
Yes.
the number of modes that you can have depends on these two parameters, on the small, because if you have a very, very small difference of refraction, then many of the modes that are launched at an angle will simply escape
Yes.
from the side.
Okay, okay. Oh,
So only one of the modes will survive.
What is it exactly known what the dermatologist sees in melanoma that you have trouble detecting using the infrared system?
So the question is about melanoma, and I read about melanoma, and the problem with melanoma is that there are tens of companies that sell instruments for early detection of melanoma. And according to a review in one of the journals in dermatology, none of the system works. There is only one thing that works, is that a qualified dermatologist or a qualified plastic surgeon looks at the body of a patient, and it takes the physician a fraction of a second, and he can look at the full body, and he says, this is suspicious. And no one knows how they do it. It's probably a combination of shape, color, or other things. So people are trying to find, so there are people who are trying to use sophisticated imaging techniques or image analysis. Other people who are trying all kinds of sensors. We simply read in the literature that no one is capable of doing what we do. Why? Because you need a fiber. Because there are many, many patients, and the patient stands, and suppose that the patient has God forbid, some lesion on the back or on the leg or whatever. You cannot use a regular spectrometer. With our fibers, we simply touch it for 10 seconds and we get the measurements. What people did is that they took, when a melanoma was removed, they froze it, crushed it, made a window and looked at the infrared transmission. And they looked for molecules like PO2 or others. It's not clear that there are these or that molecules appear. What we thought that without understanding, first of all, we'll see if we see any difference. We need a large data set. We'll probably, have 100 or so patients and see if there is a difference. If there is a difference, then we'll be able to tell. Up to now, to the best of my knowledge, no one did it what's called in vivo, clinically. Yes, on living patients, no one did good measurements of infrared absorption. And if we find some significant difference, then we'll try to see why we see a difference. But I cannot tell you now why there is a difference or there is no difference. And it's not a question of making a hypothesis. I think someone should measure it.
Any more questions? If not, let's thank the speaker. Next week, if there is not too much of a strike or something, there would be a double header. There would be two back to back.